I will be sharing about atomic convolution networks. These were introduced in the paper Atomic Convolution Networks for Predicting Protein Ligand Binding Affinity. What is the motivation or the use case for atomic convolution neural networks? So, one of the use cases is that it can be used to predict binding affinity of protein ligand complexes. In the process of drug discovery, for a drug to be effective against a target, it must bind well with the target. Traditionally, to predict the potency and binding affinity of drug-like molecules to target, it required the use of empirical scoring functions. These empirical scoring functions use hand-tuned parameters and are based on molecular force field and cheminformatic techniques, thereby requiring, in some cases, expert level knowledge. Also, for a target, there can be a large number of suitable drug candidates, small molecules, which can bind well to the target. This means that the search space for a candidate for a drug is very large. In this scenario, machine learning can help in a couple of ways. The first way, it can help in predicting the binding affinity of molecules to target by using neural networks. This can help us in so the machine learning models can learn the empirical scoring functions, and thereby it can also reduce the time taken to predict the binding affinity for a large number of molecules. Thereby it can make a search over the search space in a short amount of time. So there are a couple of challenges to use machine learning technique. The first thing, a protein or a molecule should be first represented as future vectors so that they can be learned by a neural network. To this end, the paper introduces atomic convolution Featurizer, which can futurize a molecule target into a set of future vectors, which can then be used during training of a neural network. The paper also introduces atomic convolution neural network, and the results are demonstrated by evaluating against PDBBind dataset. The rest of this tutorial are organized as follows. We will first discuss atomic convolution Featurizer, then we will discuss about atomic convolution neural network, followed by PDBBind dataset, and then we will have short demo on atomic convolution neural networks. Okay, let's see about atomic convolution Featurizer. So this ACF is atomic convolution Featurizer is used to futurize a pair of molecule target into future vectors. Broadly, the futurization computes per atom futures for each atom in the molecule, which are then aggregated to get the molecule level futures. So the first thing, the Featurizer computes a distance matrix between atoms in the molecule, the interatomic distances, and then it constructs a neighbor list for each atom. The results of these are later passed to the atomic convolution network for making predictions. First, let's see about a distance matrix. The distance matrix R measures the interatomic distance for each atom with its m closest neighbors. So we first compute the Cartesian atomic coordinates x of the molecule in the three-dimensional space. X is a n,3 matrix where n is the number of atoms in the molecule, and each entry for each atom we store the xyz coordinate in a 3D plane. So then we have R as a n,n matrix where n is the number of atoms in the molecule and m is the maximum number of neighbors to consider in the atomic convolution operation. Next, we also construct a neighbor list Z, which is used to represent what are the m atoms which are considered as the closest neighbors for each atom in the molecular system. So the Z is again an n cross m matrix where each entry is the m closest atoms for an atom. So for example, let's assume the first entry in R belongs to an atom, say some carbon atom, considering as m as 3, and assuming that the three nearest neighbors are hydrogen, carbon and oxygen, then the first row in R will be the distance between carbon, hydrogen, carbon and carbon, and then carbon and oxygen. Then the entries in Z will be used to encode what the atoms are. So this is done using their atomic numbers. So here we will be having 1, 6, 8, which are atomic numbers of hydrogen, carbon and oxygen respectively. The resultant futurized molecular system is then passed to an atom type convolution. So the atom type convolution kernel can be thought of as an expansion layer which one hot encodes the atom type into separate copies of distance matrix. For example, let's say that NAT is the number of unique atoms present in the entire molecular system, that is all the possible atoms. Then the atom type convolution takes the distance matrix R and the neighbor list Z. It then expands this matrix R using the neighbor list Z to produce an output matrix E of shape N, N, NAT. Next we have an radial pooling layer. Radial pooling is a dimensionality reduction operation. So the resultant of atom type convolution will be a very large matrix and the outputs are radially pooled. So it can be thought of as a futurization that sums up pairwise interaction between an atom and all neighboring atoms with different atom types. It takes as input tensor E of shape N, NAT, which is an output from the previous step. Then it operates on the tensor slices of 1, M, 1, which ride 1 and depth NR. So NR is the number of radial filters we have. The result which we then have is an output matrix of size N, NAT, NR. Following this, the output of radial pooling layer has shape N, NAT, NR. The matrix is flattened and the resultant shape will be then N, NAT multiplied by NR. This output is then passed row-wise to the fully connected layer to predict the energy of each atom. So once we have the energy of each atom predicted, then the energy of the molecular system will be the total energy of each atom in the system. So we sum the energy of each atom to get the energy of the molecular system. So here is a short schematic diagram of the atomic convolution layer. We have the matrix C of atomic coordinates or X as said here, and then the matrix Z of atom types. Using the coordinate matrix we compute the interatomic distance matrix R, and also we list the neighbors in the matrix Z. Using these two matrix we then perform the atom type convolution, which is an one hot encoding. We expand the matrix R using the neighbor listing Z. We just make a one hot encoding and then we pass it through a radial pooling layer, and the pooled variables are then flattened and passed to a fully connected layer to get the predicted energy for each atom. We then sum the energy of each atom to get the total energy of molecular system. So the results are evaluated using the PDBBind dataset. This dataset is a dataset of experimentally measured binding affinities for protein ligand complexes. So before getting started, a small setup which we need to do to have DeepChem and the dependencies installed. So the atomic convolution Featurizer requires two dependencies, MD-Traj and PDBFixer, which are only available as Conda packages. So we first install Conda in Google Colab, and then we install the packages MD-Traj and PDBFixer. Note that this operation might take 3 to 5 minutes, and your kernel might die. So it will restart, and when it restarts, you start by installing DeepChem, and then once it is set up, we are importing DeepChem. Since this operation will take a couple of time, I am skipping it here. The next step we have is to define the Featurizer. DeepChem has an implementation of the atomic convolution Featurizer, which we will be using for demonstration here. So this atomic convolution Featurizer takes in as features the number of atoms to consider in the candidate, the drug-like molecule, or the first fragment, the maximum number of atoms to consider in the protein, the second molecule, the maximum number of possible atoms in the complex, which is just the sum of maximum number of atoms in the first molecule and second molecule, and then we define the maximum number of neighbors, which is m in the as earlier, and we also define the neighbor cutoff. The neighbor cutoff is the maximum distance passed in angstroms for two atoms to be considered as neighbors. To load the PDBBind dataset, we use DeepChem's molecule net suite of DeepChem's molecule net API. The PDBBind dataset is available in the DeepChem suite of datasets, and hence we are loading it as it is. So we pass the atomic convolution Featurizer so that the dataset gets gets Featurized when loading, and we will be having three datasets in the variable datasets. So the first one will be the train dataset, the next one is validation dataset, and third one is the test dataset. So these were explained in the previous tutorial, so in case you are not sure about what these are, you can check out them. So let's see about train dataset. So the train dataset has got like 154 entries, and let's see a sample. So a sample has shape 9, so each sample contains some 9 entries. So what are these 9 entries? For each ligand protein pair which is passed into the atomic convolution Featurizer, it returns a number of useful geometric features. So from the documentation of DeepChem atomic convolution Featurizer, we interpret what are these geometric features. So for each molecule and the global complex is formed by combining the two molecules which are passed into it, usually the ligand and proteins. For each molecule and the global complex, it computes a coordinate matrix of size n atoms, 3, where n atoms is the number of atoms in the molecule. It also computes a neighbor list, a dictionary with n atoms elements, and elements, where the neighbor list is the list of atoms which are neighbors to an atom, and in addition it also computes a Z matrix for the molecule, which is an array of shape n atoms. So the Z matrix is just like a matrix of index that contains the atomic number of the atoms. So since the Featurization computes these three quantities for each of the two molecules and the complex, a total of 9 quantities are written for the system. So we can examine each of them. So I am storing the first molecule's coordinates in the fragment 1 coordinates and its neighbor list Z, and so on. So let's see fragment 1 coordinates. So we have the Cartesian coordinates for the molecules in fragment 1, which are represented as the X, Y, Z positions. And then followed by, we have the neighbor list. So for atom 0 in the fragment 1, we have atoms 1, 2, 6 and 49 as neighbors. So the system has around 51 neighbors. And what are those 51 atoms? So those 51 atoms atomic numbers are 6, it means they are carbon, usually carbon, and then 7, and then 8 oxygen, and then 9 I'm not sure. So once we have the fragments, then we have the dataset futurized, we can train it using an atomic convolution model. So let's define the atomic convolution model is again implemented using the DeepChem in DeepChem, and we can use its atomic con model API. We define the number of tasks, the number of predictions. So we are predicting binding affinity. So hence there is only one task which we are predicting. So we have set n task equal to 1, and then the maximum number of atoms in fragment 1, the maximum number of atoms in fragment 2, then the complex number of atoms. We also have the maximum number of neighbors, then the batch size, layer size, as well as the learning rate. So once we have this, we compute the losses and then we start training. So we store the losses in this variable and then we start training, and it's done almost. So we have, once the training gets completed, we will be having the test scores and the scores on validation dataset. So I am training here for only for 5 epochs because the training takes a lot of time. So for the brevity or for the purpose of tutorial, I am just training it for a short period, and once it is trained, we can plot the training loss and then the validation loss and see the loss decreasing over time. So as a summary, in this tutorial we have explored atomic convolution networks, and for further reading you can just see other DeepChem tutorials on molecular machine learning. So some of the references are the atomic convolution neural network paper and another DeepChem tutorial on atomic convolution neural network, a blog, and then DeepChem documentation. If you have any questions, you can post it in DeepChem Gitter channel, which hosts a number of scientists interested in deep learning, or you can also get in touch with me via Twitter or LinkedIn. Thank you.